Welcome back everyone to section number 8, right? This is related rates. In this video, we're just going over a few more problems to give us some more experience solving these related rate style questions. So in this first problem, right, I have a cone-shaped tank filling with water at a constant rate of 9 cubic feet per minute. The tank is 10 feet tall and has a base radius of 5 feet. So if you look at this picture over here, kind of makes a little more sense. And the question is, how fast is the water level rising when the water is 6 feet deep? So as I have underlined right here, right, it is a cone, so that's going to help us kind of figure out which equations to relate these values with. The next thing is that we have water is, right, it's being filled with water at a constant rate of 9 cubic feet per minute. Well, notice cubic feet, this is a unit of volume, and this is per minute, right? So this is telling you how the volume is changing. Again, it's being filled with this water at 9 cubic feet per minute. So this right here is telling you something about how the volume is changing. So if I was to go ahead and write this down into a mathematical equation, I would say the volume is changing, right? This is a rate of change, aka a derivative. So the volume is changing at 9 cubic feet per minute. Okay, we have the tank is 10 feet tall, and the base radius is 5 feet. So this is the actual structure of the tank. Remember that we are interested in really how the water level is changing, right? So kind of if I imagine inside of here, we have the water, maybe I'll use, this is purple water, kind of nasty water maybe, I don't know. So that 10 and that 5 is talking about the actual structure of the tank. But I'm really interested in things about this water cone, right? How is this changing? So the question is, how fast is the water level rising when the water is 6 feet deep? So this here water cone is going to have its own specific radiuses, right? So I'm going to go ahead and mark this R of t, and its own specific heights, right? So I'll go ahead and mark this maybe h of t. So again, it has its own radius and its own heights, and these are changing with time, right? As you add water to this, you can imagine that this cone is growing, and eventually it may even overflow. Okay, so again, the radius and the height is changing with time, and we have to be careful because that 5 and this 10, right, this is the radius and the height of the structure, right? The actual cone structure, not of really this cone of water. And this is what we're kind of interested in. Okay, so the question here, how fast is the water level rising, right? So this is talking about, again, how fast. This is a rate of change, right? So a derivative, water level rising. So this is talking about a rate of change of height, right? Because height is going to give the level of the water. So the question is, how fast is this height changing at a particular instant? And remember, so I don't have, at 3 minutes into this experiment, or when the water started running, or at 5 minutes in, or wherever, right? It doesn't specify a time. So I'm going to go ahead and use A in this case, at some time. And the thing that we know about this particular instant in time is that at this time, right, the height, or the water level, is 6 feet deep. So this is saying the height at this particular instant in time is 6. All right, so those are the things that I know so far. So I need a way to relate volume and height, right? Volume and height in particular for a cone. So I'm going to go ahead and use my volume of a cone equation. So this is going to be volume, V of t, is equal to, and if you skim back, right, to the first page of notes that we have on 2.8, you have a statement like the volume of a cone is equal to h over 3, so that's height over 3, times the area of the base. So in this case, the area of the base, well, right, it's a circle, right? So this is going to be pi r squared. We actually have the pi r squared equation under circles, right, for area of a circle. Now again, all of these things are technically changing with time. So let me go ahead and write h of t and r of t. All right, there we go. And notice that this maybe has too much, right? So we have volume, heights, and radiuses. Here I have information about volume and I have information about heights, but I don't really care about the radiuses. So I would really like to get rid of these radiuses and just have statements about height. So that's where this 5 and this 10 is going to come in. This 5 and this 10, right? I know you were waiting to see how would these be used. And if I go ahead and take this three-dimensional picture of a cone and kind of, I'm just going to look at maybe a two-dimensional equivalent really quick, kind of a cross section, right? So here's the actual cone, right? So it has height 10 and radius 5. And then if I look at the water cone, I guess I'll do this all in purple, and this has different changing radiuses and changing heights, right? So h of t here, and there's my water cone. And we see that we kind of have these kind of almost inscribed triangles, right? One triangle inside of another triangle. And this is going to be something about similar triangles, right? So that actually there's a way to relate ratios of these lengths of the sides because these are similar triangles, right? Back from our good old geometry days. Again, you see they're both right triangles and they share an angle. So these are going to be similar triangles. And so the similar triangles equation that we need to use here to kind of get rid of these h's, well, it says that 10 is to 5, 10 is to 5, as h is to r. So something like this. So again, for similar triangles, we're using the fact that ratios of side lengths of the triangles should be equal to one another. Okay, so that enables us to go ahead and rearrange, right? So I'm going to go ahead and write 2r of t, right? So that's 10 divided by 5 is 2, and I move the r of t over, is equal to h of t. And so this will enable me to get rid of my heights, right? And I can trade them, other way around. It'll enable me to get rid of my radiuses and trade them in for heights. In fact, I should probably go ahead and rearrange this and actually make it r of t is equal to h of t over 2. There we go. Because again, I really don't care about my radiuses. I'd like to get rid of those. I'd like it to all be in terms of just volumes and heights. So that being said, let's go up here and let's go ahead and simplify this down. H of t over 3, let's see, pi, and then everywhere I see a radius, I'm going to put h of t over 2. H of t over 2, and this was radius squared, so this better be squared. All right, let's do one more line to simplify things down, and then I'm going to be ready for taking the derivative. So, okay, let's see. I'm going to group together all my constants. So I have a pi, I have a 3, and I have, let's see, 2, but it's being squared, so that's going to be 4. So 3 and the 4 are both in the denominator, so that's going to make a total of 12 when I multiply those together. And then let's see, I have 1 h of t here, and then I have 2 more, right? It's being squared, all being multiplied together, so this is going to be h of t cubed. All right, now I'm ready to go ahead. I have this nicely related, so I'm going to go ahead and take the derivative on both sides. So v prime of t is equal to pi over 12. The 3 comes down, I get h of t quantity squared times h prime of t, thanks to the chain rule, right? The derivative of the inside. So that's my h prime of t. Now, let's go ahead, we can plug in v prime of t is equal to 9, right? So it's filling at 9 cubic feet per minute continuously. Let's go ahead and cancel this 3 and this 12 a little bit to get pi over 4. And now let me go ahead and plug in everywhere I see a t, I'm going to plug in my particular instant, right, my a value. Again, I don't know what time it is, but at this time, a, right, I can go ahead and plug this in. And maybe while I'm doing this, let me go ahead and rearrange this. Is going to be 36 over pi, right? So, okay, h of a squared times h prime of a. So again, I'm trying to solve for h prime of a, so I'm pretty close now. H of a is equal to 6, so if I go ahead and I square that, that's going to be equal to 36. So I'm going to have 36 over pi is equal to 36 times h prime of a, and we can see these 36's will nicely cancel out on each side. And so this will give us that h prime of a is equal to 1 over pi. Again, anytime you have one of these real-world situations, you want to include your units. So this is how is the height changing? Well, height is going to have units of feet, and the time units in this case are seconds. Right? Oh no, getting ahead of myself. They're minutes. It's much faster. So feet per minute in this case. And there we are. Of course, we could plug this into our calculator if we were allowed calculators, and right, 1 over pi is going to be around a third. All right, so around maybe like 0.3 feet per minute. Okay, one problem down. I have one more for us, and then we can go ahead and take a break. In this case, we have a balloon is rising vertically above a field. A person is 500 feet away from the spot on the ground underneath the balloon and is watching it. Right. So here's my person. Here's the balloon. Let's see. Measuring the angle of inclination, which is theta. So okay, we have the picture there. That's nice. When the angle is pi over 4 radians, right? So this is going to be changing, right? Maybe the balloon starts down here and then it keeps rising even farther than this, right? So that angle is going to be changing. That's not always going to be constant. Sometimes it's smaller, then it gets bigger, then it gets even bigger. Okay, just kind of thinking ahead a little bit. Okay, so at that particular instant when the angle is pi over 4 radians, the angle is increasing at a rate of 1/10 radians per minute. At that moment, how fast is the balloon rising? All right, so we need to go ahead and maybe write down some of these statements into mathematical equations, and then figure out what we have and what we need to determine which equation that we should use. So here we have at a particular instant of time, right, that theta value is equal to pi over 4. So this is not constant, but at a particular instant of time, that theta value is equal to pi over 4. So I'm going to say that there's some theta that depends on time. And at a particular instant of time, that theta value is pi over 4. So in the previous problems, I've been denoting this a particular instant of time with a. Right? But again, if you're like physicsy and stuff, you can use maybe t sub 1, for instance. Okay, at that particular instant of time, the angle is increasing, right? So this is talking about a rate of change, increasing and decreasing, right? So, okay, it's increasing at 1/10 radians per minute. So again, this is telling us how the angle is changing. So this is going to be the derivative of theta at that particular instant of time. That's going to be 1/10. Okay, and then at that particular moment, how fast is the balloon rising? So if I go ahead up here and I say that this is maybe the height of the balloon or something like this, we want to know how fast is the balloon rising. So in order to win this game, right, I want h prime at that particular instant, right? So it says at that moment. So at this value in time, which I'm going to denote with a, I want to know how fast is the balloon rising. So that's how I'm going to answer this question. So I have thetas here. It looks like I need something with the heights. And I actually know a little bit more, right? I know that this is a constant 500 feet, right? This person isn't moving. They're not getting closer to the balloon or farther away or anything like this. So I need an equation that relates together this theta value, this height value, and I do know something about this side right here. So a theta value, a height value, and this, it's a nice right triangle in this case. So the one that comes to mind is tangent, right? Because tangent of theta is supposed to be opposite over adjacent. So opposite over adjacent. So in this case, that 500 is nice and constant. Now remember, my theta, right, is changing with time. So really, to be a little bit more precise, let me go ahead and write tangent of theta of t. Right, so that theta is changing with time here. Okay, now I'm ready to go ahead and solve. Again, the first thing that I would want to do is take the derivative, because notice I have a lot of rates to relate together, right? Related rates. All right, so if I take the derivative, on the right-hand side, I'll do the easy one first. That's h prime of t divided by 500. And notice I'm keeping this, this is technically like 1 over 500, right? So this is a constant that's along for the ride. Sometimes I see people use the quotient rule, which will definitely work. It'll just take a lot longer, right? So this 1 over 500 right here is a constant. It's along for the ride. So I'm using the constant multiple rule here. Okay, on the left-hand side, well, I have the derivative of tangent. Well, that's going to be secant squared. Leave the inside alone. Multiply by the derivative of the inside. The derivative of the inside, well, that's going to be theta prime of t. So that's the chain rule there. Now I'm interested in a very particular instant of time, right? So I'm going to plug in a everywhere I see a t. So this is going to be secant squared times theta of, secant squared of theta of a. times theta prime of A is equal to h prime of A divided by 500. Remember, I'm trying to figure out how fast is the balloon rising at this particular instant. So I'm going to be trying to solve for this h prime of A. Okay, at this particular instant of time, we know that theta of A is equal to pi over 4. So this is going to be secant squared of pi over 4. And that this is equal to 1/10, right? That theta value is changing at 1/10 radians per what, minute? Radians per minute, yes. And now let me go ahead and solve for h prime of A. I'm going to multiply by 500 on both sides. There we go. So now you can see I've basically solved this. The only question is, what is secant squared of pi over 4? So, all right. So this is again where we need to be good friends with our unit circle. So let me first maybe start off with cosine of pi over 4. Because remember, secant and cosine, they're friends, right? Secant is 1 over cosine, or the reciprocal of cosine. So, okay, cosine of pi over 4, that's going to be root 2 over 2. So therefore, secant of pi over 4, remember this is the reciprocal, or 1 over. So this is going to be 2 over root 2. And in fact, if you rationalize this denominator by multiplying by root 2 over root 2, something nice happens here. Right? So again, this root 2 times root 2, this is just 2. So that 2 on the bottom will cancel with this 2 on top, and actually all you're left with is just root 2. So that's secant. Now notice I have secant squared. So if I square both sides, I'll get that secant squared of pi over 4 is equal to, well, if I square this side, I'll just get 2. So in this case, it actually all works out fairly nicely. Secant squared of pi over 4 is just 2. So this is 2. I still have this 500 out here and this 1/10 over here. Again, this is how the balloon is, the height of the balloon is changing at this particular instant. I can go ahead, let's see, 1/10 times 500, that's going to be 50. 50 times 2 is going to be 100. And now I need to think about units, right? So let's see, we have units of height would be something like feet, right? So I have feet here, and then how it's changing. So I need a unit of time. I have per minute. So, okay, this is going to be feet per minute. All right, and that is my final answer. There we are, and that is it for 2.8. Good luck on your homework. I'll see you guys next time.